Hello everyone, it's a pleasure meeting you all in my mathematics class. Today I continue with doing problems in partial differential equations, and this is my lecture class 4 in PDE. Lecture class 4 in PDE. This is a in PDE. So this is the problem that is given to us. I used to tell you, or rather if you watch my videos in partial differential equations, I would have said that given a problem, we have to use the appropriate transformations to bring the given differential equation to a form about which we know how to write the solution. So this was what I was telling in all my videos. Today also I am going to do the same thing. So what I am going to do here is, this is given to us. This is a differential equation involving p, q and z, x, y, everything there. I want to reduce by using a proper transformation to a form whose solution I can write immediately. That is what I am going to do. Now, here you see that. See, given. So what are you given here? P squared plus q squared is equal to z squared into x squared plus y squared. So this is what we are given, and here you are given only this p, which is nothing but dou z by dou x, and q, which is nothing but dou z by dou y, and z is a function of x naught. And we have to solve for z, where z is a solution. Z is solution. And from this, we have to get the value of z in terms of x and y. That is finding the solution. Now, here we are given only this p and q and also this one. So what I do here is, I divide throughout by z square. So when you divide this throughout by z square, you will get p squared z to the power of minus 2 plus q squared z to the power of minus 2 is equal to x squared plus y squared. I divide throughout by z squared, because of which I am getting this. So this simply implies it is p z to the power of minus 1 whole square plus q z to the power of minus 1 whole square is equal to x squared plus y squared. So this is what I get. Then again I am telling you that use a proper transformation to bring it to a standard form whose solution is known to us or immediately can be written. So here it is. Now let me use a transformation like this. So I will call this as my 1. Let us suppose that we are using a transformation capital Z, which is equal to log Z. I take in this way. So this implies dou Z by dou small z is equal to 1 by z, or dou small z divided by dou capital Z is equal to z. Now, see, now dou z by dou x, which is nothing but our p, this can be written as dou z by dou capital Z into dou capital Z by dou x. I am giving a transformation only for z. This is what I get. So this is nothing but, I will call this, see here, dou z by, so in this place I can write this as z into capital P, where capital P is nothing but dou z divided by dou small x. So this simply implies, so what is this? So that is P is equal to Z. So this implies capital P is equal to P into Z to the power of minus 1. Therefore, P square is equal to P into Z to the power of minus 1 whole square. So you can see that this is P Z to the power of minus 1 whole square. Here I have got this. So in the place of this P Z to the power, I can substitute here Z square. So in a similar fashion, what you have to do is, so therefore, and I will write here, see, dou Z by dou Y, which is equal to Q. This is nothing but dou Z by dou capital Z in dou capital Z by dou Y, which is nothing but, see here again it is Z into Q, and therefore Q is equal to ZQ, which implies Q is equal to Q into Z to the power of minus 1. This implies Q squared is equal to QZ minus 1 whole square, where Q is equal to dou capital Z. So you see that I am able to giving a transformation, I will be able to bring it to a different form. So I will use this, see, this one, and use this one. So I will call this as my 2 and call this as my 3. So I will substitute 2 and 3 in 1, so that I will be able to identify it in the form I want to. Okay. So substituting, see I write here, substitute 2 and 3 in 1. So let me substitute 2 and 3 in 1. So what is that we will get here if you substitute? So this will become P square plus Q square is equal to X square plus Y square. So this is what you will get here. So in the place of this P Z to the power of minus the whole square, I will step C, it is here. See, this is what you are. So in the place of this, you put P square, in the place of this you put Q square, that is equal to X square plus Y square. So I am able to bring it to a form and another differential equation whose solution I know how to write. Okay, so what I will do here is, this implies P square minus X square is equal to Y square minus Q square. Now you must know that this P is dou Z. See, what is your P now? P is equal to dou capital Z by dou X. Q is equal to dou capital Z by dou Y. Now you see that this is nothing but dou Z by dou X whole square minus X square, whereas these two are independent of each other, but they are equal to one another, They are equal to each other and they are independent of each other. This can happen only when I can take, when this is so, I can take each equal to A square. I will repeat this because this place is very, very important to understand. This is these two factors here, P square minus X square and Y square minus Q square, they are independent of each other. So that is, they do not have it. They are equal, but they are independent. If such a situation comes, we can make each one equal to, this simply tells us that it is equal to a common factor. It is equal to a common factor. These two are equal. That can happen only if they are equal to a common factor. So I am taking the common factor as a squared. You can take a or a squared, any constant. So a is a constant. So here a is a constant. See? A is a constant. So this simply implies, say each one, see this means p squared minus a squared is equal to a squared. This implies your p squared is equal to x squared plus a squared. And y squared minus q squared is equal to a squared. With this implies your q squared is equal to y squared minus x squared. Y squared minus a squared. So these two are important. Now, see, having got this, as I told you, I bring it to a certain place by using, yes, that is, I bring it to a form using a particular transformation so that the solution can be written. Now, I am able to bring it to a standard form. So, using this, I am able to get the value of p squared and this one. Therefore, see, therefore, so these two, you see, these two imply p is equal to x squared plus a squared. Square root of this q is equal to y squared minus a squared square root of this. So this I will call it as 4. So we will call it as 4. Already we have written 2, 3, now it is 4. But we know that using total derivative, you see that this dz is nothing but it is p dx plus q dy. Because if you take the total derivative of dz, it is dz is equal to where this p and q are this. What is this p? P is nothing but dou capital Z by dou x. Q is equal to dou capital Z by dou y. So this is nothing but this capital P is your dou Z by dou x and Q is dou Z by dou y. But in turn their values are this x squared. So this is this is the equation that we are having. So in this equation you can write d. See, this is capital Z. This is not small z because we have changed it. So dou d capital Z is equal to, in the place of, that is dou Z by dou x. But dou Z by dou x is equal to P, which is equal to x squared plus a squared square root of this into dx, plus similarly this is y squared minus a squared into dy. Now we have got this. Now you see that this is nothing but what? This is some x involving x. Integration is equal to the differential is dx. This is involving only y. The differential is dy. Now you see that it is nothing but, now you can simply integrate, you will get it. So integrating this simply implies integral of d capital Z is equal to integral of x squared plus a squared square root of this into dx plus integral of y squared minus b squared into dy plus necessarily a constant of integration. Now you see that I got the solution. So use a proper transformation, bring it to a form whose solution can, so that the solution can be written immediately, about which we know. So I know what is what, so I have done it. Now I am able to get the solution. Now you see that for you it is only simply you have to go for integral. You have to apply the, see, you can give, these are all standard integrals. These are all standard integrals. I will apply the results immediately. In your university examination also, you can straight away apply the results. You need not go, you struggle to get the integral values, because this will take a longer time for you to integrate. Definitely I will do this. I will just work it out and tell you how this integrals have to be evaluated. But I make it clear that in university examinations, or even otherwise also, when you come to this part, you can immediately apply the integral value, and you need not elaborately do it because this will consume a lot of time. These two will consume a lot of time, but you can just apply the results. So this is now the solutions. So we have got this. See, this is, I will call this as my 5. So 5 is a solution. So I got the solution to the problem. Now you integrate on both sides, you get. Now what is the integral value? So therefore we get, see, therefore we get, so this 4 gives 4. 4 gives, see, if you integrate, it becomes capital Z. And the integral value of this is x by 2 into x squared plus a squared, square root of this, plus a squared by 2 into sine h minus 1 of x by a, then plus it is y by 2 into y squared minus a squared minus a squared by 2 into cos h. This is cos h minus 1 of y by a plus the constant variable. So I will just check it out because from my memory I have written this. I will just find out whether this is okay. So this is what you get. So x by 2 plus square root of this plus a squared by 2 sin h minus 1 of this plus y by 2 then minus a squared by 2. So this is perfect. So you see that this is the solution. Now this is not this is the solution when for the transformed problem, in the sense that after taking small z is equal to log z, this is a solution. But the solution for the original problem, what is the solution for the, see, this is our original problem. See, this is our actually original problem. This is our original problem. Therefore, solution for 1, that is the original problem. So z is equal to what? We have taken z is equal to, see, log z. So put in the place of this log z. So log z is equal to x by 2 x squared plus a squared plus a squared by 2 sin h minus 1 of x by a plus y by 2 y squared minus a squared minus a squared by 2 cos h minus 1 of x by a plus b. This is called the complete solution. Complete solution. To find, I'll call this as my 5. We will call this as our 5, or we will call this as capital 2 like this. See, to find the general solution, take, see, you take this b is equal to f of a, b as a function of a, then see b and function and differentiate. B is equal to f of a, and then differentiate to find the value of this a, because we have to find the value of the constants here. So you take this b is equal to f of a and differentiate this with respect to a. If you differentiate with respect to a, you see that you will get another equation involving, you differentiate that and solve the resulting equation and this too for a. I'll repeat this. You take b is equal to f of a and differentiate with respect to a. And the resulting solution you take, solve for b, the resulting solution and the solution 2, you will get the value. So such a solution. So to find the general solution, take b as b is equal to f of a, differentiate with respect to a, call the resulting equation as 3, solve 2 and 3, solve 2 and 3 for a. For a. So you solve, you call this guy as 2, take b is equal to f of a, differentiate, and then use the two equations to get the value of a. Then you get the simple solution. Now, if 2 is differentiated with respect to b, if you are going to differentiate this with respect to b, the left hand side is 0, here everything will be 0, but differentiation of b with respect to itself is 1 is equal to 0, which is absurd. See, this is absurd quantity. Therefore, no singular solution. No singular solution exists for. So that's all.